The first thing we're going to kind of talk about is what a definite integral is. For the purposes of this class, integral and antiderivative are kind of going to be the same word. They're slightly different in context, but we're going to use them pretty much interchangeably. Really what this does is it gives us a way to find the actual area under a curve. So if we went back and talked to Riemann about his rectangles, this would be like if we could actually push the rectangles all the way to infinity, we'd actually be getting this area formula. We're going to figure out how to do these with calculus in the next couple of class periods. But for right now, we're going to have to rely on our current knowledge of area. We're just kind of putting some notation on top. So the actual area under our curve is equal to that definite integral. And here's our notation. That is an integral symbol. It's like a really long S, but shouldn't be as fat as an S. If you want the computer option, though I did a decent job drawing that one, it's right there. I'm going to put these numbers on it. I know they look like letters, but they will be numbers in our question. Those two numbers are called bounds. Sometimes they're called limits as well. I usually stick to the verbiage bounds because we already have another thing that is a limit.
Like when you do that, like 1 is less than or equal to x.
Yeah, so kind of like an interval you could think of. It's kind of telling us we're taking our area from A up to B. And I could write that as like a compound inequality if I wanted to. You could also write that in interval notation. That's often how we'll see it in this class. But it gives me a start and an end to my integral process. The rest of this is our function. So whatever function we will be integrating is going to be in there. That essentially means whatever function we are finding the area. There has been a fly in here all day. All right, sorry. This function inside has a cute little name. So if this is an integral, this guy is the integrand. Just like radical and radicand, it's like whatever's inside there. And then we're going to end with a dx. You can kind of think of the dx as part of your notation here. So I like to think of the integral symbol with the bounds as like the front end parentheses and the dx in the end as the back end of a set of parentheses. So they kind of go together. And once we learn how to integrate a function, once I integrate, those two things will be gone. That guy's name is a differential. Notationally, that is very similar to our delta x that we were working with the Riemann sums. So it kind of changes to that dx when it becomes infinitely small. And we still have our height here from our rectangles. That was a function value. So it's kind of like we still have our base times our height here. What? Antiderivative. Yeah, it's got some fun words in here. So really, this is just putting some new words on what we were already able to do. We are going to not actually evaluate the definite integral. I shouldn't be using that word. We are going to approximate it using a right endpoint Riemann sum with 6 subintervals. And then we're going to evaluate it by drawing a picture. Thrilling. All right, let's make ourselves a table. So I want to take area from what number to what number. So looking, yeah, I want to go from -2 to 1. So -2 to 1 is my interval. And I want to go from -2 up to 1 in 6 steps because I have 6 subintervals. Count by 0.5. Do you guys like that? All right. One way I could also find that if I want to be a little more methodical. So I could do 1 minus -2. So the end minus the beginning over the number of intervals. That's 3/6, which is indeed, I'm going to go with 1/2 instead of 0.5 because I am solidly team fractions. Is anyone else team fractions? No. Depends on the context. All right. Well. All right. So I'm going to start at -2, and I'm going to count up by 1/2. So I'm going to count -3/2, which is also -1.5, -1, -1/2, or -0.5, 0. Oh, 1/2. You know, it's kind of like those fitness tracker reminders for you to get up and stand up every once in a while. All right, I want to know, normally here when I'm making my table, I plug into some sort of function. What function should I be plugging into to find y values here? 2x. Yeah, that dx is kind of notational, so he's just going to stay at the end until we integrate our function. All right, so how good are we at multiplying by 2? Because those are our x values. No, I'm what? What is 2x? That's our function that we're working with. So whatever function we're working with is inside that integral. Mm-hmm. Yeah, so we're working with like the function y equals 2x. All right, we're just going to plug these numbers into 2x. So what am I going to write under -2? All right, next one. -3. Just get rid of the half. -2. Do we see a pattern? Fast. Whoa. All right. All right, as I start this Riemann sum, I know I've got 6 subintervals. What's the other word that I need to pay attention to in this question? Right endpoint. All right, so let's see if we can set this up. If we wanted to kind of get really, really fancy with our notation, we could take our integral, our definite integral. What makes it definite versus indefinite is having those bounds. And we're going to say that this is approximately equal to our work for our Riemann sum. Now, the first rectangle, I'm going to kind of highlight what we're looking at for that first rectangle. How long is he along the x-axis? So our delta x. 1/2. All right. And then what f of x or y value are 2x values? Which one are we going to use? -3, the one on the right. All right, let's do one more together, and then I'll set you off to kind of finish up setting them up. How long is the next one along the x-axis? 1/2. We set these up to be equidistant along the x-axis, so literally all of our delta x's will be 1/2. How tall will the next guy be? Sorry, not tall, not along the x-axis. What function value will I use? Will I use -3 or -2? -2, the one on the right. All right. We've done 2 of them. We've got 4 more to go. Are they all going to be 1/2 long? Okay. I'll die on the fraction fill. So, all right. 1, 2, 3, 4, 5, 6. I always feel a little bad when I write off the paper because I know you guys can't do that. Sorry. I am cheating.
I mean, we can. It doesn't help.
Yeah. All right. What's the next function value I'm going to use after -2? -1. Can I just keep going? 0, 1. What? Oh, you're telling me the actual answer? All right, so let's look at, this would be something I would be comfortable asking you to evaluate without the use of a calculator, because a lot of stuff cancels. Does anyone see anything that's going to cancel out as I try to add up some stuff? All right, the 1 and the -1, those guys will cancel. The -2 and 2. And the 0 is not going to be there. So Herbie threw out a number earlier, and that number was -3/2. Now I'm changing my equal sign here because now I'm claiming that this guy equals this guy. You could keep your approximately equals whatever you want. There's something kind of weird about this. Does anyone remember graphically what we were finding with this? What were we approximating? Yeah, we're approximating the definite integral, which means area. Have we heard of negative area before? Let's figure out. So let's draw a picture of this really quick. I think Derek's got the answer. What? Okay, so I'm listening to you guys say something about being under, and what are you talking about being under? That was a vague question. That was poorly worded. All right, let's draw a picture, and I'm going to try to phrase my question a little better because I'm not phrasing it right. So I'm going to draw a picture of our graph. What does the graph of 2x look like? Yeah, it's a line. Goes up this way. I have a dot on the origin because that's its y-intercept. Has a slope of +2. So when I said area under a curve, I actually was doing a pretty poor job describing what an integral actually is. Hello. All right. So that's true when I'm above the x-axis, like right here. So this area I do want. That kind of corresponds to some of these triangles over at, or some of these rectangles over at the end. Do you think I want like all of this stuff down here though, below that? No. I actually should be talking about the area between my curve and the x-axis. So I'm going to kind of go and make a note of that back up at the top. But what do you notice? You guys were talking about above and below, probably that x-axis. What do you notice about kind of these shapes here, if you will? The one below the x-axis is bigger. So when we talk about area for integrals, we're going to be talking about signed area, meaning that anything below the x-axis is going to count as negative. Anything above the x-axis is going to count as positive. And then I just kind of want to make a note for under here. We're talking about between our curve and the x-axis. And I realize we're doing one that's not a curve right now. Usually our things are going to be curvy because usually we're going to need calculus to find these things. So what we actually found was not these two shapes. We actually found the rectangles that I'm kind of drawing in right now.
So what's the dx do?
So the dx is kind of like our delta x. When we get to actually integrating and doing antiderivatives, it's not going to look like it really does much. So it's more so a piece of notation, but it goes back to the idea that this was our delta x, so that's kind of like our dx, and this guy was our f of x value, or in this case 2x. So you can kind of see that we've got the 2x times the delta x inside our integral. For us, though, when we do problems, it's very much going to function as a piece of notation. All right, so good questions all around. The question I would like to ask you now is, do you think you actually need calculus to find the area between this curve and the x-axis? What shapes do you see? Triangles. Do you need calculus to find the area of two triangles? No. Yeah, you can use geometry. So when I was saying we were going to use geometry for the first half of class, I literally wasn't lying. We're really going to use the idea of area, and a lot of the things we're going to look at today will be things that are geometrical in nature, where we have formulas for their areas, and we're going to actually be able to evaluate without learning the calculus behind the integral. So for the first half of these notes, the only calculus you're doing is knowing that that cool symbol right there means take the area of this curve from here to here. So my first, what is the area of a triangle, by the way? 1/2 base times height. So let's do it for these two triangles. The base, I'm going to use the base to be along the x-axis. So for this one that's under the x-axis, I'm going to do 1/2 2 times, how tall is he? 4. And since that guy's under the x-axis, I'm going to add a negative sign. All right. So we're using this guy right here. What? All right, we have to add on the other triangle. It will be -4 for that one. We've got 1/2. What two numbers am I going to multiply for this guy above? 1 times 2. All right. Herbie's right that the first triangle is -4 plus, that's not 2, that's 1. And we get -3. So notice this guy is our approximation and this guy is our actual. We didn't do a great job at approximating. Yeah, so we could make it better by doing smaller rectangles, definitely. But why do that when we can actually evaluate it? So we're going to take a hot second to draw some pictures. Then we're going to get some properties and combine all of it. So let's see what we know about graphs. So here we're working with the function f of x or y. I'll write y just to make it easier. Y equals 4. Can you take your arm and graph the line y equals 4? All right, there's an argument. Which arm is correct? This one. All right, so let's draw it. We got a graph. 1, 2, 3. It goes through 4, right? All right, I've got this beautiful picture. Where am I going to and from on the x-axis? So I'm going from 1 up to 3. So I'm going to kind of block that off with a little bit of a vertical line right here. Yeah, what shape do you guys see? It's a rectangle. Is that base times height like Herbie's telling me? Yep. So we're going to go 2 times 4. This is 8. Done. So the calculus I'm using is the knowledge that this notation means area. All right, let's draw another picture. Yep, our function is y equals x plus 2. Perfect. So Herbie's telling me my y-intercept is 2. Yeah. If in doubt, what you can do is make yourself a little table. So don't freak out. You know exactly what values you should be plugging in because you've got 0 up to 3. So you could plug in 0, 1, 2, 3 and give yourself some points. This is 2, 3, 4, 5. So 4, 5. Here's a dot here. 1, 2, 3. Yeah. All right, so I've got a straight line. All right, so Herbie's right, it is a trapezoid. Does anyone remember the trapezoid area formula? We were just using it. Yeah, so let's say that's blurry. Let's say you're like, I'm not loving a trapezoid. My only goal is to find this area. So does anyone see a way I could get around using the trapezoid area formula? Yeah, why not? We can cut it up. As long as we can add those together, we can find the answer. So I'm going to do that because I'm lazy and I don't want to use the trapezoid area formula. So the rectangle on the bottom is 3 by 2. The triangle at the top, I'm going to do 1/2 base times height. The base is 3 and the height is from 2 up to 5. So it's also 3. So I've got 6 plus 9 halves. 6 is 12 halves. So I think 21 over 2, or if you're Derek, 10.5. All right, let's look at some other graphs that are a little bit harder, but we do kind of know how to draw them, but we'll use a little bit of Desmos to help us out. Does anyone know what the next one looks like? The square root of?
It'd be
Yeah. All for exponential.
yeah, but like a half.
All right, a half curve maybe. All right, let's graph it on Desmos real quick. You cannot, unfortunately, because those are being added. All right, So math's a good question. Can I simplify these by taking the square root of both? I cannot because we're subtracting. So I'm kind of stuck using the square root of 4 minus x squared. I want to show you a picture of it though, and I want to show you why the picture looks like it does. Desmos. All right. SQRT 4 minus x squared. What's that?
What?
A half circle. All right. What do you think the 4 is? How does that 4 help us?
How long?
All right. It gives us technically the radius squared. So 2 squared here. That's giving us the radius. So if I change this to a 9, what's the radius going to be? 3. All right. Interesting definition of big. I could make it 16 and have 4. Here we have this guy right here. Do we need calculus to find the area of this? No. Oh, also bonus question. What happens if I put a negative in front of the square root? What do you guys think will happen? Whoa. Transformations. They're amazing. If you wanted to know why that works, remember that I could say y equals the square root of 4 minus x squared. Let's say I squared both sides and I added the x squared over. Does this formula look more familiar? X squared plus y squared equals r squared. If anyone cares. All right, so let's draw ourselves a little picture. Not bad. All right. And we're looking for the area bound between our curve and the x-axis. So that's going to be that half circle right there. Now, does anyone remember the area of a whole circle? Exactly. I'm going to do pi halves r squared because I'm weird like that. And what did we say the radius of this semicircle was? 2. All right. Square that, we get 4 divided by 2. I think this whole thing is 2 pi. This one's actually kind of interesting in general. There's going to be a lot of things that we can integrate, but there's also going to be a lot of things that we can't integrate once we start getting into the calculus of all of this. This actually happens to be one thing that we're not going to be able to integrate, but we can do using the idea of area. So it's kind of interesting, depending on your definition of interesting. Integrating? Yes, I think so. I have one specific integral I do when I'm bored. It's great. Fun. All right, does anyone remember what absolute value stuff looks like? Yeah, it looks like a V. A good way to find where that V is, we'll look at this one. Does anyone know anything about this specific V shape? Anything about it at all? All right, a good way to figure out where like the point of the V is to set this guy equal to 0. Because what absolute value does is it switches kind of the sides of the V once I go from negative numbers to positive numbers, because absolute value changes those negative numbers to positive numbers. So this guy's going to flip at 1/2. We can look at that in a second on Desmos as well. That must sound terrible on the recording when I do that. Anyone actually watch them? Who knows? Oh, there. If you go on the Schoology page.
Except one day when I was sick, you put it up like halfway through something.
It's right there. You click this, and it's like a channel.
You are so awesome. I didn't want to, but someone
have 20 subscribers right now. Most of them are the academic team. Shout out academic team. All right. So I don't do it for Algebra 1 because I don't think anyone watches. But I do it for BC as well. All right. So notice here that 0.5. Derek's reminded me that is equivalent to 1/2 a couple of times now. So that's where we're flipping through. Again, let's say we were nervous that we didn't know what this graph looked like. We found that 1/2. You can make yourself a table. So if I were making myself a little table to help myself graph this, so my X and my Y values, I could plug in like 0, 1, and 2 to get a couple more pieces of information. If I plug in 0, I'm getting the absolute value of -1, which is 1. 1, I would just get the absolute value of +1. Notice that that 1/2 between there is going to be on the x-axis, and then 2 times 2 minus 1, that's 3. So you can always get yourself a little bit more information that way.
How did this equal the different values?
Because you have this one is absolute valuing to get that 1, and this one is just staying that value to be 1. All right, so we have 3 here. Oh wait, I shouldn't be at 3 there. It's at 2. All right, so I'm doing a quick sketch. All right, do I need calculus to find the area between this and the x-axis? No, what shapes are they? 2 of them. All right, so I've got 1/2. What are the base and the height of that tiny guy?
1/2 base, 1 height.
Cool. And then the bigger guy, 1/2 what times what? 1.5 times 3. I'm gonna, instead of if you're Derek, maybe you do 1.5. I'm gonna do 3/2. All right, so I've got a 1/4 plus 9/4, which is 10/4 or 5/2. I love fractions, man. It's so cool. All right. So now that we've got the idea of geometry, the idea of if something's under the x-axis, we can call it negative. Let's add on one more little thing, and then we're going to almost be at our break. This is the harder part of class, though. All right. Some properties. Anytime we learn something new, we want to know what's legal, what's not legal. Some of these have very good geometrical interpretations of why they are true. Some of them just intuitively feel true. So first one with a very good geometrical representation. Is geometrical a word? I've said it multiple times now. It doesn't feel right. Okay, cool. Quinn says it's right. All right, let's say I have this curve and I'm finding area from A to A. How much area am I going to accumulate? 0. So if you have the same bounds top and bottom, your integral is 0. No matter what bounds they are, if they're the same, you have accumulated 0 area, 0. All right. The other one that has a good interpretation, and we use this one a lot in BC calculus, is let's say I had the area from A to B, but then I wanted to slice it down the middle. Would you agree the area from A to B is the same thing if I take the area from A to C and then add the area from C to B? Yeah. So it's a kind of obnoxious to write, but I'm going to do it anyway. Notice that as I write each of these integrals individually has, oh, I shouldn't write B at the top. I meant to write a C. Excuse me. Notice each of these integrals separately has its own dx. Again, that dx is functioning like, for us, kind of like a closing parenthesis on that integral. So you're going to open with the integral sign, end with the dx. So that'll contain your f of x. What? So this, oh, the one above it. Anyone notice something kind of weird about the one above it? Yeah, it looks like it's going backwards. So let's say I wanted to flip the bounds. This one's kind of intuitive. What do you think? Yeah, that's exactly it. If I want to flip the bounds, I'm going to make it negative. All right, the last one. I shoved a k in here. Where else do you think I could write the k, which is the k for constant? I could write it on the outside. Okay, so I think the second and the fourth ones are kind of intuitive in nature. The first and the third ones have pretty good geometry behind them. Yes. Yes, but not in this class. In Quinn's class, yes. When you start doing multiple integrals, you can do double and triple integrals with multiple variables. Yes, you can put variables in the bound because for individual integrals, they'll be considered constants. For us, they will always be numbers. All right. Actually, two things I want to be very clear about. We are not dealing with any multiplication or division of functions inside, and we won't deal with that this year very much. So just be aware that I can't just like break things up willy-nilly, but let's do some practice on our own. I would like you to try to take the 4 properties we just talked about. This is very AP in style. I've given you 2 pieces of information that this integral equals 4, this integral equals 1. I want you to try to use those 4 properties to answer 1, 2, 3, 4, and if you're feeling spicy, number 5. Number 5, I believe I stole from a test. Is the answer he's wrong? He's correct? I know. Yeah. Did you see his question about like why he has to do weighted averages in the first place? It's at the very bottom. He's like asking us to check his work and then being like, hey, also. Oh, I love that I'm recording this conversation and posting it on the internet. Hopefully he doesn't look for me. Sorry, Graham. I think it's just that we don't have like, we think his data is weird because we don't know the way his job works. Yeah. It's that neither of us know what the other one knows, like at all. You should. All right. I'm going to talk to you guys about these in 2 minutes. Anyone really confident about any of them yet?
Yes.
The first one?
Yeah.
That's what I thought.
All of them look one.
Really weird to be planning graduation right now.
You're planning graduation.
That is correct. Yes. Seems like it, right? It's a little bit distressing to me because I'm like, I have so much left to teach. And then I'm like, but it's almost summer. And then it's kind of not.
It's not even spring.
Yeah, what is official spring?
Like, up here,
March 20 something? Yeah.
March 21st, 22nd, 23rd.
Wait, anyone confident about number 5 yet? I'm excited. All right. Who's confident about any of these? The first 4? All right, someone tell me one of them.
0.
Number 1 is 0. Excellent. Number 2 is what? Negative 1. All right, so we flipped the bounds on this one. So we made negative 1.
3, 4 are 5.
3 and 4 are both 5.
Yeah.
I disagree with one of those. You think 3 is 5? Oh, you think 3 is 3. All right, let's look. So this property, number 3, is taking advantage of the fact that we want to split this into 2 pieces. We want to go from 0 to, not 6, we want to go from 0 to probably break it at 3 because they're giving us a lot of information about 3. And we want to add on from 3 to 6. All right. Yeah, this is 4, but be careful. Is this the same thing as this? No. So we actually want to add on what we did in number 2. So we're adding on negative 1. So Derek is correct. We are going to get 3. All right. I do like 5 for number 4, though. That one is 3 to 6. So we're taking, again, our answer from number 2. And we're doing negative 5 times negative 1 to get positive 5. All right, anyone want to venture a guess for this guy? 36. That's what I got. All right, so looking at this one, we have, what could I steal for the f of x? I'm going to steal the answer from number 3 probably. So 2 times my answer from number 3, which was 3, minus 3 times what they gave me right here is negative 10. So that's 6 plus 30, which is indeed 36. They have put a lot of these on the multiple choice practice that they put out recently. So just take it step by step. All right, the last thing we're going to do before we take a solid break is this last question that kind of puts it all together. So these are very popular on the free response part of the AP test. So we're going to find 2 values of a function g of x that is an integral. So notice we get this weird function g of x. There's a couple weird things about it. 1, it's an integral. 2, the x part of it, the piece that we plug in, is in that top bound. So it's a little bit weird. Also, we have this t here, which is a little bit strange. This t is just kind of a holder variable because we have the x up in a bound. So it could be any letter you want. It could be H for Herbie, D for Derek, M for Matt, whatever you wanted, as long as it's not the x that's up in the bound. So we're going to do this twice, and then we are going to take a break. If you're wondering what this type of function is called, it's called an accumulation function, and I actually really like that name. Because it gives us a good idea of what this function does. It essentially accumulates area from 1 to wherever we plug in. So let's look first at g of 2. Just like I would if I were in Algebra 1, Algebra 2, pre-cal, whatever, I'm going to take that x value and put it where x is. So I'm going to go from 1 now to 2 of f of t dt. Now, the t does not change any of my method here. I'm still going to look at my picture and try to find the area from 1 to 2. So here's 1, here's 2. I can draw any vertical lines I want to kind of cut off my areas. I should not be adding any more horizontal lines in. So what shape do you think I'm going to be finding? A triangle. Perfect. All right. I know the area of that triangle is 1/2 base times height. We're going to find that base and that height in a second. Is there anything else you want to tell me about that area? Negative. Why is that area going to be negative? Perfect. Love it. All right. What are your thoughts on the base and the height? All right. Base is 1. What's the height? Are you sure? All right, let's look. We have points here. We could find the slope of this, right? So we go down 1 and over 2, right? You are. I just want to make sure. We don't want to assume anything based off of our graph. So if we only went down 1, we would be going over 1/2. So we get negative 1/4. If you prefer. All right, let's try this one. Again, first step, I'm going to put that number where the X was. Personally, for me, I become immediately uncomfortable. Does anyone think they know why I am uncomfortable? Yeah, I'm going like the wrong way. We have the rule. I would like to flip-flop these bounds so that I'm going from left to right. Herbie is correct. I need to add my negative sign. As I do my areas now, I'm going to be really lazy and kind of just have a negative sign and some humongous parentheses. All right, let's look at where we're at. -2 up to 1. Let me use a different color. Again, you can cut off your areas with any vertical lines you want to draw, but you should not be adding any horizontal lines. You can draw along the x-axis as well if that helps to cut off your areas. So looking at this, we're talking about this triangle and this semicircle. Now, I do know that's a semicircle and these are line segments. They actually did tell us that. They were really specific and said line segment, semicircle, because we're not allowed to assume anything based off the graph. All right, thoughts on that triangle? One times 3. Yeah, I like that. All right. Any thoughts on that semicircle? Ooh, good. Negatives. So he's on top of our negatives, which is great. Those are super, super easy to miss. Pi 1 squared. I almost love it. Is that a whole circle? 0.5 pi times 1 squared. Now, the cool part, once we start practicing for the AP test, which we will start doing soon, on the free responses, you do not have to simplify. So as soon as you get it here, we could be done. We don't have to do any of the math from there. If you are like me and you get creeped out or you just want to practice, you could distribute your negative. So I'm going to put the negative pi over 2 out front, and then you would subtract the 3 halves. Definitely not necessary. You could definitely leave it where it is. All right, cool. Let's take, I'm going to go, you guys have been very nice and been listening. We're going to take a 6-minute break. You've been participating. You've been good people. Yes, you may take 12 half-minute breaks. Ooh, should I judge the science fair? I think the answer to that is no. And why not? Because I have too many things. Too many things on my plate. Yeah. Kind of crazy. We're very close to the end of the year. We only have 8 units. We're like halfway through 6.
What?
Yeah.
When do we finish usually?
So we'll finish right around spring break. We'll spend between spring break and the AP test reviewing. And then my seniors are probably leaving me. Are all the seniors doing outreach? You don't know? Oh. You should. They'll make sure you must. Dr. Luttrell wants you all to leave. And then we'll, AB will probably learn some easy BC, depending on how busy I am with graduation. Yeah, what are you gonna do? You're gonna have to sit by yourself when they leave.
Be happy.
Yeah.
Sorry, Mallory. You copied me. Happy birthday.
Yeah, I'll have to plan out because our AP test is kind of late. We still have like a month. There'll probably be a couple days we get to go out and put out chairs for graduation. It'll be exciting. Okay. Should we do? Probably not today, but we might open with one next time. Do you want me to do another one like this? I have another one on the notes that I was going to skip, but I can do it.
Yeah.
Okay.
Also, I have a school on 3 to 5.
You can sit over there. No one.
How do we know where I'm
They still showed it. Kindergarten class. I don't know. He's not one of my sources.
So we use essentially 0 to 3.
I have 3 sources inside the FS.
Start here to here.
Don't you say.
All the way from.
Do it. Are you really? What you should be? Are you going?
This one's for the guy, so if we have a constant multiple.
What do you do here? This is not hard. Actually, no, you're supposed to do it in between. Yeah.
Thank you for letting me re-explain.
And also you close. You have to find your dominant eye, right? You close your non-dominant eye. And then you realistic. And then you open it before you shoot. That's not what real life is like. How would you? That's what happened. Did you know that they closed their line before they shoot it?
What are you talking about? Okay.
I was a sniper. I used to be a sniper, yeah. To be a mom. I was a sniper. Yeah. The sniper. I was doing a raid on I was doing this. I was doing those ones. Go ahead.
All right. So just to review what we did before break, just in case you were feeling uncomfortable, these are super popular on the AP test. So I'm just going to run through this one really quick. Notice this graph is a little bit easier because it's all triangles. I don't have to worry about any semicircles. That's not the case usually on the AP test. They usually like to chuck a semicircle in. But just to get this idea back in our heads, I'll do these two. So we're going to find G of 2 and G of 10. What I'm going to do first, plug in my bounds. Yeah, does anyone already know the answer? It's 0 because the bounds are the same. Don't even need the graph for that. I'm guessing for G of 10, I'm going to need the graph. So again, I'm going to put those numbers where the X is. And the only calculus knowledge we're using today is, hey, that means find the area between this curve that we've got in our picture and the X-axis. So looking from 2 to 10, What shapes do you think we're looking at? Triangles, specifically this triangle and this triangle. Notice that when I'm drawing lines, my lines are either the lines that are on the paper or the x-axis. So some people are always tempted to like do this. Don't do that. Why do you think it's 0, Herbie? Yeah, so they're the same size triangle, except one is above the x-axis, counts as positive area, and one's below the x-axis, counts as negative area. I could just write equals 0, but let's just practice with the area formulas. My triangle is 1/2 base times height. All right, both 4s. So from 2 to 6 and then up to that y value. And then I would be subtracting the other triangle. It's below the x-axis, 4 and 4. All right, so multiple ways to get 0. If you're thinking of this one, it's kind of like if we're finding displacement, kind of to connect back to that, it's kind of like we ran forward and then ran backwards. So we would have a total displacement of 0. All right, so you may be wondering to yourself, well, what if that isn't a shape I know the geometry of? What if it's curvy? What if it's weird? So we're going to have to use calculus for that to do something with the function. And what we're going to end up doing is called an antiderivative. Now, this is going to feel very unrelated to what we just did. And that's because I'm going to bring it together next class with something called the fundamental theorem of calculus. So I'm going to give this to you guys as a challenge. I have not taught you how to do this explicitly, so I want you to go into this with kind of a investigatory. You're kind of like a detective. I don't want you to think that you already know how to do this. You're trying to kind of figure it out. So don't be afraid of being wrong is mostly what I'm trying to say. We'll do the first one together just so I can show you what this notation means. So think antiderivative. That means kind of the opposite of taking a derivative. So what I want us to think of is what function did I have to take the derivative of to get this thing as the derivative? So what did I have to take the derivative of to get 2x? Okay, I want you to try to investigate some of these down here. Now, some of them are harder than others. Some of them are going to require a little bit of finagling, if you will. I'm going to give you 5 minutes to just try to think it out, get as many as you can. If you get one done, great. If you get none, but you're kind of noodling on it, that's cool. If you get all of them, fantastic. If you want me to check any of them, let me know. So you're exactly, it's doing a derivative but backwards. We're going to eventually have rules for this, but I want you to know why the rules are the way they are. It may help to think of how we took derivatives. We normally took the power down, multiplied by it, and subtracted 1 from our exponent. So consider that antiderivatives are the opposite. Does anyone know their derivatives? Some of them?
Sorry.
I'm on. Yeah, it's fine. Yeah.
If we introduce to college.
You guys are going to try anything?
Super.
Okay, so you think that one would be like 3 at the top?
One half. One half x to the x. Yeah.
That one is.
Shut it.
Oh, a lot of ideas.
Attacking.
Sometimes, great people.
You know what?
Oh, you are you.
Base.
I get the opposite of this.
Except the book
X
Squared.
Yeah, one half x.
As soon as you start saying about
Dude, wait, I got it.
Yo!
Oh, yeah.
Are we able to solve this one just for like putting this?
Best thing is
Because if I write down like -2.
alright.
Now my hands are. All right. Anyone feeling confident about any of them?
The second one.
The second one, what did you think for the second one, Herbie? X to the 4th. Does that work, everyone? We bring down the 4, we subtract 1, 4x cubed. All right, cool. I like it. Anyone confident about any of the other ones? Matt, what do you got? The x squared one?
Yeah.
What did you get?
I did 1/3 x to the third.
1/3 x to the 3rd. Does that work? You want to put your phone away? Thanks. All right, the 1/3, brilliant move. When I bring down the 3, 3 times 1/3 gets rid of that coefficient, so we just have x squared. I love it. In that vein, and was anyone commenting about what they got for x? All right, I like the 1/2 x squared. When I bring down that 2, the 2 and the 1/2 will cancel. If I subtract 1, I've got x to the 1st. All right. Anyone know who has the derivative of cosine x? Regular sine x. Does anyone remember who had a derivative that looked kind of like cosecant squared? So cotangent x was the one that looked similar, but derivative of cotangent x was not cosecant squared. What was it? Negatives? Exactly. All right. Now, these ones, as I walked by, I think it was Herbie trying to figure out this one. He said, wouldn't it be nice if this we rewrote and brought it up to the top? Anyone have an idea of what we could do here? What does it look like we've been doing to the powers? Looks like we've been adding one, right? So looks like the power should be -2 because I would subtract 1 to get -3. All right, I like the 1/2, and I'm actually going to steal, Derek said, a negative. So we can do -1/2 times -2 to get that no coefficient or that 1 on top. How did we rewrite square root of x often? X to the 1/2. Evan, you got this one, right? What did you come up with? All right, let's see if that works. If I bring the 3/2 down, does 3/2 times 2/3 give me just 1? So no coefficient? Yeah, brilliant idea there. And then the 3/2 minus 1 or 3/2 minus 2/2 will give me the 1/2. Did anyone try this one?
No.
All right, we did x already. What would x be? All right. What did you? Okay. That is actually all the way right. All right, so let's get some ideas down on the paper. I do have one question before we actually write down the rules. And this is kind of a vague question. I'm hoping for a specific answer. Let me know if you want me to rephrase. The question I would like to ask you is, are these the only things I could have written down? That was a quick no. Why did you say no?
Because, like, for example,
I could add a number. So I could have had x squared plus 1. I could have had sine x plus 5. The derivative of every single number is 0. We have to account for that, but we don't know what that number was because every number has a derivative of 0. So when we go to write these rules down, after every single antiderivative, you're going to see a big old plus c. That c stands for a constant. So let's go ahead and we're going to write some of these rules down. I'm also going to show you the notation for doing this antiderivative process. You're going to notice it looks very similar to what we did at the beginning of the day. All right, this is what the notation looks like. Is anything kind of glaringly obvious or like missing? It's the same thing with no bounds. So this is called an indefinite integral. Again, we're kind of using the word integral and antiderivative relatively loosely the same. There's slight differences in how you would talk about them, but for the purposes of this class, they're going to be essentially synonyms. So let's just kind of write down these rules. We'll try a couple from down here and then we'll be done. I don't have a notes check for you. So what things have derivative of 0? We just talked about it. Any number, so any constant. So if you integrate 0, you're getting a constant. Let's say I integrate a constant. So like I integrate 2 here. What would go after that k? Kx and then plus c. I need to account for a constant in every single integral I do. This rule is still true even if I don't have bounds. I can move that k out front of my integral. That's perfectly fine. I can also split the integral over addition or subtraction. So the sum or difference of two functions inside my integral, I can do the two integrals separately and then add or subtract them together. This one's kind of annoying to write. Notice again that we will put a dx at the end of each of our integrals. Really, all of these rules that I've just written down, including the next one we're going to write down, which is bigger because it's more important, are building us up to being able to integrate a polynomial function. So I have how do I deal with a constant? How do I deal with a constant multiple? How do I deal with addition and subtraction? And this one is essentially our new power rule. What did you guys say for these ones? What was I doing to get the new power? It was adding 1, right? And then how did I get this number out front? Yeah, I'm kind of dividing by that number or multiplying by the reciprocal of that number. So one way you can write this, I'll write it a couple of ways for however you prefer to think about it in your brain. a lot of textbooks will write it like this, and I'm going to throw my plus C over there, where you have add 1 to the power and divide by new power. Or a lot of the time I'll write this out front because I like to have my fractions kind of out front rather than behind. But notice this is the exact opposite process of taking the derivative. So for our derivative, we multiplied by the power and then we subtracted 1. Here we're doing the actual inverse process of both of those. So we first add 1 and then we divide by the power. So think of it kind of like solving equations where you have to do exactly the opposite way. All right. Last thing is our trig derivatives. For these right now, what you only can do for trig derivatives is essentially just notice them. So what thing had a derivative of cosine? Sine. All right. What thing had a derivative of sine? Negative cosine. I will tell you, I hate it so much that these negatives are in the opposite place as the derivatives were. I can't change mathematics, but I wish I could. What thing had a derivative of secant squared? Regular tangent. All right, so if you didn't know your trig derivatives, now's a good time to go and memorize them. What thing had a derivative of secant tangent? Regular secant. All right, we did cosecant squared already. It was negative cotangent. And then what's the only one left? Cosecant, you think is positive or negative? I want you to notice all of these things are, whatchamacallit, single trig functions. So I'm never going to integrate trig right now and get multiple trig functions out. Also something cute. What do you notice about all the ones that start with C? They're negative. All right. To end class today, I actually want to show you a mnemonic or a little helpful thing that I think it was Nina showed me. Nina Segura, if you know her, she's a senior. She reminded me of this little thing that helps you remember the trig derivatives, especially these secant and tangent ones. So if you write this, secant, secant, tangent, cosecant, cosecant, cotangent. So if you're taking the derivative of tangent, it's secant squared. If you're taking the derivative of secant, it's secant tangent. Kind of cute, kind of helpful. Cosecant, cosecant, cotangent. So if you need help memorizing those, that's pretty much it. All right, let's just try to do one before we leave. So power rule. We're going to add 1, divide by new power. So 3/5 x to the 5th. All right, what will the new power on 5x squared be? 3. What? 5 over 3. All right, what will the new power on x be? 2. What number should I put out front? All right, why is my answer not right? Plus C. All right, we'll practice more with these next time. I will probably give us just a minute to practice all of these before we learn how to connect this with bounds and area. If you would like to pick up your new problem set, I will put them in the middle of the room. Or should I just walk around with them? They're green or spring. You'll notice this problem set's a little bit longer because this chapter is a little bit more important than the ones that we've done in the past. This and the extrema chapter are the most technical we have. There are quite a few things that you can already do. For me, thank you. I will have dates for you next time. We will. Notice we have a quiz on 6-1 to 6-3 that will be happening next week. Happy weekend, y'all.
I can